All right, let's dive into something we all deal with every single day, the water that comes out of our taps. We're going to pull back the curtain on the science that answers a really important question. How do we actually know that our water is safe to drink?
You turn on the faucet and the water runs out, looks crystal clear. But what does clear really mean? That simple question is the driving force behind the entire science of water quality testing, and it's exactly what we're going to break down.
So before we can even think about testing water, we've got to get on the same page with the language. Our journey starts with understanding a really crucial difference. What's just in the water versus what's actually harming it. Okay, so here's the first kind of surprising thing. An impurity is literally just anything in the water that isn't a water molecule. And hey, that's not always a bad thing. Some impurities, like minerals or dissolved oxygen, are actually essential for fish to live and can even be good for us. A pollutant, on the other hand, well, that's an impurity that's crossed a line. Its concentration is high enough that it could cause harm for whatever we're using the water for, like drinking. You see, the goal isn't to have sterile, lab-grade H2O coming out of our taps. That would be totally unnatural, and frankly, it would taste pretty weird. The real goal is to have water that's perfectly safe for its purpose. It really all boils down to concentration and context. So how in the world do scientists check the quality of an entire lake or a whole river? I mean, they can't test every single drop, right? Well, the secret is in capturing a tiny but incredibly accurate snapshot of the whole picture. The key to this whole thing is something called a representative sample. Think of it like a political poll, where they interview a small, carefully chosen group of people to understand what an entire country might be thinking. Scientists do the exact same thing, just with water, collecting a small amount that's chosen to perfectly reflect the health of the entire river or lake. And there's not just one way to do it. Scientists usually pick between two main strategies. A grab sample is pretty much what it sounds like, a single snapshot in time. It's perfect for measuring things that can change really fast, like temperature. But a composite sample, now that's more like a time-lapse photo. It's made by combining a bunch of grab samples taken over a period of time, maybe 24 hours, to give a much better average picture of the water's quality. Which one they choose really just depends on the question they're trying to answer. And let me tell you, this isn't as simple as just dipping a bottle in a stream. It is a super precise, standardized procedure. From picking the exact location and the right kind of container, to preserving the sample by keeping it cold and tracking it with a strict chain of custody, every single step is designed to make sure the sample that gets to the lab is exactly the way it was in the river. All right, so our sample has been carefully collected, preserved, and shipped off. Now, for the fun part, let's follow it into the lab and see what secrets it's hiding. To get a quick but really powerful overview of a water sample's health, labs often start with three basic tests. We're going to look at pH, conductivity, and turbidity, and believe me, together they tell a surprisingly detailed story. First up, we've got pH, which stands for potential of hydrogen. To put it simply, it's just a way to measure how acidic or basic the water is. And this one little number has huge consequences for everything from the fish living in the water to whether our pipes start to corrode. The pH scale is pretty simple. It runs from 0 to 14. Right in the middle is 7, which is perfectly neutral. Anything below 7 is acidic, and anything above 7 is basic. Now, for our drinking water, regulators want it in that near-neutral sweet spot, usually somewhere between 6.5 and 9.5. That keeps it safe for us and helps protect the pipes delivering it. Next up is conductivity, and this one is super interesting. Get this, totally pure water is actually a terrible conductor of electricity. So, a conductivity test measures how well a water sample can pass an electrical current. If it gets a high reading, that means there's a lot of dissolved stuff, like salts and minerals, in the water, which lets that electricity flow. And this table gives you a fantastic sense of scale. I mean, just look at the difference. Pure water is practically 0. But seawater, which is just packed with salt, can have a reading of 50,000 or even higher. Our tap water is right there in the middle. It's a really powerful, really quick way to see how much stuff is dissolved in a sample. And finally, we've got turbidity. Honestly, the easiest way to think about this is just as a measure of water clarity. It's a number that tells us how cloudy the water is because of all the tiny particles, like clay, silt, or even bacteria, that are just floating around in there, scattering light. And here's why this is so important. It's not just about whether the water looks nice. High turbidity is a major red flag. Why? Because those little suspended particles act like tiny shields for dangerous pathogens, hiding them from disinfectants like chlorine. It can also be a dead giveaway for pollution runoff. So yeah, it's a critical measurement, both for our health and for the environment.
And while labs have all kinds of high-tech gear, there are also some brilliantly simple tools for this. This is the Secchi disk. Scientists just lower it down into a lake until they can't see it anymore. The depth where it disappears gives them a quick, effective, and really low-tech estimate of the lake's turbidity right there on the spot. Pretty clever.
Okay, so we followed our sample from the river into the lab, and we've gotten our results. But what happens next? This is really the most important part of the whole story. How all of that data gets turned into actual, real-world protection for all of us.
See, all these measurements, the pH, the conductivity, the turbidity, they're not just for some academic paper. They form the scientific backbone of our public health regulations. This is the data that scientists and regulators use to set clear, enforceable safety limits for the water we drink, the lakes we swim in, and the water our industries use every day.
Here's a perfect real-world example. For treated drinking water, the turbidity limit is often set at 1.0. It's called a nephelometric turbidity unit, or NTU. Now, that's not some random number. It's a scientifically proven threshold that helps guarantee any harmful microbes that might have been hiding in the water have been effectively zapped and removed. That little number is basically a guardian of your health.
So, what are the big takeaways here? First, clean water isn't pure water. It's safely managed water. Second, how you take the sample, whether it's a quick snapshot or a long-term average, totally depends on the question you're asking. Third, a few simple tests can tell an incredibly complex story about water's health. And probably the most important thing, this science translates directly into the safety standards that keep all of us safe every single day.
So I'll leave you with this to think about. The next time you pour a glass of water, just take a second and think about the incredible scientific journey that little bit of water has been on. What invisible story of science, sampling, and safety is it telling you?